Cool, thanks for coming. It's good to see such a good turnout. Thanks, Teddy. Hopefully that feedback goes away. As she said, I'm going to be talking about a study on gaps we've been working on. I'll be talking about it, but I've been doing the work with a lot of other folks. I just want to acknowledge that it's been a really good division and region collaboration. Lots of people have helped set the study up and execute it, so I just want to give a shout out there. So the idea starts with the notion of we manage for multiple objectives on state lands, certainly on the OESF. Revenue production's a big one. Also habitat is arguably the other big one. And some of that involves providing some of these more complex structured forests that's associated with late successional or old growth forest. Yeah. And so we manage different stands in different ways with that in mind, and where our habitat objectives involve sort of late successional structure, some features of that are easier to provide than others. Like if you want a giant candelabra-topped cedar tree, you need 500 years, and there's not much else you can do about that. But other features we might actually be able to manage for. So now sort of the cartoonized version of those two pictures I showed. One of the more promising treatments that a lot of different land management agencies have been trying is this idea of gaps. You see, we have the simple even age structure and a competitive exclusion stand. This is where we produce a lot of our timber volume. The old forest structure tends to have these holes in it where trees have grown up into. Mortality and recruitment process is happening at fine scales. And so there's areas where we want to move these stands closer to that direction. And we can't make old growth out of second growth instantly, but we can maybe do some things to break up that simple canopy and move it in that direction. So when we started this project a while back, Bill and Drew and others, they told us they had been implementing gaps within VDTs. This is an example from a variable density thinning early 2000s where they had been punching in half-acre gaps. This is kind of standard. They are, one objective for those is to help the sale pay for itself, to get more volume out. And another objective is to break up that, you can see on the landscape here, it's a very homogeneous second growth canopy, so it provides some kind of canopy diversity. But there's a couple unknowns associated with this. One is, so these gaps were put in, and then nothing was planted or veg control wasn't done. So it's sort of like what happens when you punch a half-acre hole in a windward Olympic Peninsula forest and just walk. There was some concern that they could turn into brush holes, or we could lose them as productive ground for some time. The other uncertainty was, is this the best way to do it? If we're trying to move toward that late successional forest structure, basically we're shooting without a target. Everybody is, all the agencies doing this because there is no target. We don't know. There's not very good data on the size distribution of natural gaps in old growth forests. So it's hard to know if you're being accurate, efficient when you don't have a target. So we got to thinking about the process that actually creates gaps in older forests. Of course, we have fine scale things like individual tree mortality, tree fall. And then we also are working in the coastal zone here that is largely a wind-driven system. So we have that process also creating gaps. So as an example, this is a photo of an actual wind-generated gap that was, I believe, created in the 2007 storm. This is on state lands. So, and you can already kind of appreciate some things there, that the edge is very messy. There's remnant trees in the middle. There's lots of dead wood. There's recruitment and root wads. So there's probably some things we can learn and glean from these. So we set up this study in 3 phases. The first one was just to go back to those old gaps after they've been growing there for a decade at the time we started this study. So we had that opportunity to go back, over a decade later and see what had happened in those. And then, like I said, trying to get some sort of reference information from old forest gaps to see if there's something we can learn about how to implement them better. And then apply what we learned in the second phase to an experiment. So first I'll walk through the first phase. And this is going to be kind of a high-level pass because there's 3 phases of the study and I have like 10 minutes left. So I'll give you some highlights from each of the phases. So we went back to these gaps and we just asked basic things like, what's the tree recruitment there? How's it growing? How's the other vegetation responding? Are we seeing branching and crown responses from the trees, the overstory trees around the edges? Are we seeing expansion and contraction of gaps through wind events and so on? So we went through about 20 of these gaps and we did this design. So, you know, we're not in the tropics, we're in the temperate latitudes where the sun comes in at an angle. So we have this south to north series of plots, because you can imagine the light coming in might affect the north edge of the gap different than the south edge. And then we had these 3 reference plots out in the thin forest matrix. So keep that in mind. We'll spend some time with this kind of graph. I'll show you a few of these. So here's just a reminder of that plot layout. And this is basically turning it on its side and going from those 2 southerly plots in the thin forest through the gap to the north and then up to this plot, which is there. So this is just the percent of plots that are occupied by trees at least 100 trees per acre. So you can see there's a real gap response, pretty apparent there, that we go up to about 90% of the plots that we sampled were in fact occupied by trees. In terms of density, there was a wide variation. So not, like I say, not every single plot was occupied. So there were gaps with no trees in them. But there were also gaps where you could barely walk through them because they were so full of hemlock regeneration. And then if we look at these numerically, so there's a little bit of surprising amount of advanced regen of small stature in just the regular thin forest out there. But there's a clear gap response again with the mean, 1,500 to over 2,000 trees per acre. So on average, trees are definitely coming in here. So I guess maybe it's no surprise the west side of the Olympic Peninsula, if you punch a hole in the forest, trees come back. It's pretty hard to keep them out. Similarly, characteristic for the peninsula is the hemlock. This is the composition of the trees in the understory. And so the main thing to take away is that this dark purple color is hemlock. It's pretty much all hemlock in the thin forest. Mostly that in the gaps, but we're getting a little blip of some species diversity, mostly silver fir and a little bit of Doug fir. So now moving away from trees to the shrubs. So this is the other thing that people wondered about here. And the answer is yes, shrubs definitely respond to holes in the forest here in a big way. Their percent cover ranges from 80% to over 100, meaning there's so much cover that it's actually overlapping itself. So there is a shrub response, and on average, I'm not showing that, but I believe it's in the 2 or 3 meters tall, so 6 to 10 feet tall range typically. So in spite of that, the tree height growth, which I'm showing here, is actually okay. It's not the 3 feet a year or plus that we can get out in plantations in this part of the world, but they're not stagnating, and they're sort of on their way to a free to grow status. So I don't have time to go through every single thing that we're looking at here, but I wanted to at least mention, like I say, we're looking for this idea of trees along the edges might self-prune less, so their canopies might lengthen, their branches may extend further out into the gap, so we might get longer, deeper and broader crown architecture in these adjacent trees. So we're testing that hypothesis. And we're also looking for things like epicormic branching as new light is hitting the boles here, which creates habitat platforms for things like murrelets and other arboreal wildlife. So, and we compared them, we did a systematic sample of edge trees and compared them to random trees within the forest. And the short version of that story is we are starting to see a response. It's pretty clear in the graphs, but it's not significant yet. It's probably going to take, it's a slow response, so it's going to take probably another decade to really manifest. All right, so those are some quick highlights from phase 1. I want to go through some things from phase 2. Learning about old growth gaps. So we were asking, what is the range of gap sizes we tend to see in natural old growth forests? What are the range of gap shapes? And how are they spatially distributed in terms of density and clustering, connectivity? So you'll hear about this a lot later today. Among the new remote sensing tools we're using is LiDAR, which is amazing. We've reprocessed some of the LiDAR flights from out here. And this is an actual aerial view down onto a forest here. So LiDAR is the laser version of radar, basically, if anyone doesn't know. That's flying planes over, shooting the forest with lasers and getting the bounce back. And it tells you, creates a point cloud of where all the forest structures are. You'll hear lots about this later. So we've coded this image for where the ground level is yellow going up to blue to the highest tree crowns. And you can see how every tree crown really pops out. It's really clear. And you can see different tree heights in there. And so, of course, if you can see the tree heights, you can also see the trees. You can see the places between the trees, which is what we're interested here. So it sounds simple until you actually have to do it. How do you define a gap? Does it have to be all the way down at the ground level? Well, no, you can have some regeneration within a gap. Probably everybody would agree that. Well, how high is too high then? So we had to make all these sort of judgment calls about what a gap is. Turns out there's actually some industry standards, so we were able to sort of make sure we're on the same page, which is good. There's some other things about the spatial definition of a gap. So some of them are pretty clear, like that one I highlighted in red there. It's pretty discrete, right? But what about this one? You start drawing that, it's like, is that the end of that gap? Or is actually, well, it actually keeps going. It's like, well, and then you look at that and you say, is that functionally all one gap? Is that how wildlife view this? Or, you know, we don't know. So again, there's some industry standard ways to try and define what a distinct gap is. So some initial results from this. This is ongoing. The thing about this particular phase, which is really fun, is that the tools are constantly changing, and the ways that we can use LiDAR and the ways we can approximate where tree crowns are, which I think the remote sensing folks will talk about later. So we're always sort of revisiting this, and it's ongoing. But so quickly, just kind of what we found in terms of gap sizes. So this is the size of gaps here on the x-axis and how frequent they are on the y. And there's a real clear pattern that these small gaps, less than like 1/8 of an acre, are really by far and away account for like 80% of the gaps out there or more. So 1/4 acre, they're present but few, and 1/2 acre gets pretty rare actually, as it turns out. In terms of shape, we were surprised to find that on average they are much longer than wide. They're long and skinny, which may reflect tree fall as the primary gap forming process. So one hypothesis at least. And the density per acre we're still working on. I only highlighted a few here just for demonstration, but you can see there's tons of them in here. So. Okay, so there's some quick things from phase 2, which like I say is ongoing. So we had a strict timeline for this study. We had to get an experiment going for a variety of reasons. So we wanted to take those initial findings from that phase 2 and apply them to an experiment. I can get this thing to keep working. Okay. So in this experimental phase, we were just asking, okay, if we put in some different gap shapes. This was just a cartoon in our proposal. We had no idea what phase 2 would tell us what those shapes would be. So these were just sort of spitballing. What is the influence of the shape of the gaps and their orientation on things like the veg and tree recruitment? Basically all the same responses from that phase 1 measure, part of the study. So with the help of Bill and Drew and Cody Pagel, we identified a variable density thin sail, the Tacoma Select. It's down on Queets Ridge. A little over 400 acres. I think it ended up being, it was in a 35 to 40-year-old second growth Doug fir hemlock. And our plan was to collect before data, immediately after data, and then do a 5 to 10 year remeasurement cycle eventually. So this is a close-up sort of drawing of one of the units. So basically, we went to each of these units and we split each one into 3 different treatments, and then we randomly assigned each treatment, each block to a treatment. So that's what it looks like here. So we split it into the control, which is just thinned but with no gaps, the traditional round gaps, and the new long and skinny gaps, their 4:1 length ratio that I told you about. And we did each one in 2 sizes, 1/8 and 1/4 acre, because those were more common. Much smaller than that becomes operationally not really that relevant, and much larger than that is very rare. So we thought we'd try these. Right, so we replicated this in 3 different blocks. So this is just an aerial view of one of these blocks. That's the pre-treatment image and the post-treatment image. So, oh yeah, and incidentally, here's the half-acre gaps from a prior study, prior VDT back in the day. So yeah, so here's that 1/8 and 1/4 acre round gaps and 1/8 and 1/4 acre long skinny gaps. And then the control is down here. And just a quick visual of what some of these look like. I'm not showing any data from this because they're super boring. It's just pre-treatment, it was super homogeneous second growth. I mean, we sampled the heck out of it just to be statistically rigorous with like 80 some odd pre-treatment plots, but they were all exactly the same. It's like the mean is here and the standard deviation is right there. It's just classic second growth, really dense, not much understory. This is post-treatment, so I'm just showing this so you can see not only is there a thinned forest back here, but it's also, this is the edge of a gap that you can see just as an example. And again, the post-treatment data, again, are very interesting because they show that yes, we thinned the forest, there's less trees than there were before, and yes, we created some gaps. So yeah, there's over 200 plots total now. We did that same sort of south to north sampling, except we added plots here at the northern and southern edge to see if that gap influence is extending into the forest a bit with light coming in from the edge. And then the orange plots there are the sort of like fully in the matrix thinned only plots. And then we repeated that along the long skinny. So we did the pre-treatment sampling in 2015, the harvest then occurred over the next couple of years, and then we finished the post-treatment sampling just last fall. So that data just came in, and like I say, it just shows that we did the treatment. So the plan now is to monitor, and the only interesting responses will start to manifest at the next remeasurement cycle, hopefully. So ongoing, like I say, we're still going through refined methodologies and trying to get less distracted from other projects to work on the phase 2, the old forest part of the study. And then we'll go back to the phase 1 and phase 3 observational and experimental gaps and see how they're developing over time. So, and then we want to use remote sensing like aerial imagery and so on to look for gap expansion. Maybe the long skinny gaps are expanding or not expanding in a different way than the round gaps. So that's all I have.